doing it. I would just keep like energy in as positive, but and just make that positive for everything. But I mean, no matter what it is, you have to be careful about it. So why not be careful about it the way it is, you know?
Sure. But I guess when you think about it in the context of that, energy in is positive. Because if you do work, right, like you're adding in the equation, right? Like if I do work on a piston, the energy goes up within the.
That's right. But you just have to have the double negative. I mean, yeah. It's just something to get used to. Okay, so now we're going to talk about simple compressible substances. And every material we'll discuss in this class is a simple compressible substance. I'll abbreviate that, simple compressible substance. And what it takes to be a simple compressible substance is it has to be homogeneous. Anyone know what homogeneous means?
Well mixed.
Yeah, that's right. Just so you can't go from one spot to another spot and see different stuff. Everything's the same, right? Like homogenized milk, you know, like they mix it so you don't have.
They just like put it through a blender.
Yeah, just a blender, and like before they do that, there's like over here there's like blood, and here there's like parts of a hoof, you know. But then they blend it, and it's all the same.
Yeah. Thankfully, I'm lactose intolerant.
Oh, yeah. So it has to be homogeneous, and it has to be unaffected by electric and magnetic fields.
Now, those are like definitions of a simple.
Yes, that's right. Fields. And what we'd like to have with these what we want for these are complete equations of state. And so what those mean is relationships between different properties at a single state, at any state. It turns out that at any state, two properties of a simple compressible substance simple compressible substance is enough to fix all the other properties in that state. So what I mean by that is if you know the temperature and the pressure, say, then you won't have any multiple possibilities for entropy, enthalpy, specific volume. All those other properties are fixed. That doesn't mean we always know what they are, but we'll have some different approaches for figuring out the relationships between those. And when a simple compressible substance is in a saturation state, and so the meaning of a saturation state is undergoing phase change. Then one property is enough to fix all the other properties. The position, specific volume, and temperature of any simple compressible substance can be shown on a PVT diagram. Or a PVT surface. And there are two slightly different versions of this. I mean, they all have different versions of this, but there are two sort of, there are two qualitatively different versions of this. So there are two slightly different types of PVT surface. One is basically everything except water, and then the other one is water. Water is a weird thing, actually. So the first one, insert a picture. Good thing my desktop is so well organized. So PVT, not water. So this is basically everything. And what you see in this case is at a single pressure. So just to get your orientation here, pressure is up, specific volume is horizontal, and then temperature is back. And so specific pressure is just a specific height. And what you see is that I'm not aware of any other substances except water that that doesn't act this way. But what you get is when you go from so you go from gas to liquid, and then when you go to solid, you get a decrease in the specific volume. Okay, like something freezing normally makes the volume go down. Okay. So this is every material except water. Freezing decreases the specific volume. Now for water,
And it causes this season of construction.
yeah, that's true. For water, I don't want you there. You come over here. You can see it does the opposite. Very strange.
So temperature changes in materials that aren't water just lead to like expanding and contracting.
For including water, everything
Opposite. To water.
just opposite. So for water, freezing increases the specific volume.
But everything else is kind of the same.
Yeah. And water just happens to find a funny crystallization shape where it makes extra space for itself. And the amazing thing is a lot of life depends on this because, so like for example, when lakes freeze, water freezes in the winter, if yeah, it would kill all the fish because so the way we have it now, water that starts to freeze, so the coldest water, as it starts to freeze, becomes less dense, floats to the surface. The water underneath is the warmer water, and it prevents most of the lake from, it's what keeps a lake from freezing solid. If it was like the cold air above froze the top surface, it got more dense, it sank to the bottom, and it would just happen like that until the whole lake was a block of ice. And whatever. There's a lot of animals that wouldn't be able to survive that. All animals, except water bears. But that's a story for another time.
Tardigrades?
Yeah, right. Exactly. Water bears. And we're usually going to, it's pretty hard to work with these 3D surfaces, so we're not going to actually use this in any meaningful way. But what we are going to use is projections of these. So when we use these, we'll use projections onto a single plane because it's pretty hard to draw and think in 3D from a two-dimensional image. So here's the kind of thing that we're going to see. Okay, so, this is just so you have the PVT surface in the middle, and that just shows you like what a projection looks like onto a pressure temperature diagram over on the left, and then what it looks like on a pressure volume diagram on the other side. And you can do all these different projections, and they all have different uses. The most important feature on these projections and it appears on almost every projection, So the PVT surface and almost every projection is called the vapor dome. And it always looks something like this in every one of these diagrams. You can see it on the PVT surfaces there. Okay. And it represents the phase changes. This line at the bottom is called the triple line. This red dot at the top, the peak of this dome, is called the critical point. Over on this side, when a material is in any of those states, it's called a saturated liquid. A material that's in any of these states is called a saturated vapor. And if you're to the left of the saturated liquid line, you're in a solid state. No, you're not. That is wrong. You're in a liquid state. If you're inside here, you're a mix of liquid and vapor. And I'm just going to use gas and vapor interchangeably. And then if you're to the right of the saturated vapor line, you're a vapor. So let me tell you what some of these terms mean. So the triple line.
And what axes again are we looking at?
Really, it almost doesn't matter. In almost every pair of properties, you see something like this. But I'll talk about a couple of specific ones after I go through these meanings. But the triple line means solid, liquid, and vapor can all exist in equilibrium. The critical point, the top of that dome, is the pressure and temperature above which liquid and vapor there's no longer any distinction between liquid and vapor. So there's no distinction between liquid and vapor. And this screaming hot, high pressure stuff is just called a supercritical fluid. And there are some power generation plants that take advantage of the properties of supercritical fluids. But we're not really going to work with that.
What's the significance that the triple point becomes a line and the critical point stays a point, like moving from 2D to 3D?
What's the significance of that? I guess,
like looking at
yeah,
it from a different
I guess the critical point only depends on the pressure and temperature. That triple line is a point in any on any one of those projections you choose. No, that's not true. I don't know. I'd have to think about that. Okay, so critical point. The next one is a saturated liquid. And a saturated liquid is a liquid where any additional energy causes a change to vapor. So it's on the boiling line. And a saturated vapor is a material that's in a vapor state where any reduction in energy causes a change to liquid.
How do they express those?
Well, for like a given pressure, it's just given by a temperature. So like what we're used to with water is a saturated liquid at atmospheric pressure would be 0 Celsius. No, would be no. I keep getting that wrong. It would be 100 Celsius liquid. Okay, so if you add a little more energy to that, it starts to boil. Okay, and a saturated vapor would be 100 Celsius vapor, completely gas, but any reduction in energy is going to make it condense into a liquid.
Are they rates though? Like if the energy is constant, the temperature is, X?
They are, well, think of, by energy, I'm talking about internal energy. So it's like a property that this thing has. It has a certain amount of internal energy. And if you give it a little more, it boosts it into a vapor. Or if you give a saturated vapor, if you take a little away, then it becomes a liquid.
Got it. Okay.
And the last thing, saturated vapor, the last definition I need to give you is a superheated vapor. And that is vapor above its boiling point. I think a lot of us grow up thinking of steam as being sort of like visible, um, because when we see steam, we boil a teapot or something. Uh, we get that um, we get that saturated liquid into a boiling state, and then the gas that comes out, the steam, is vapor at 100 degrees Celsius, and so it's that's a saturated vapor that comes out of the teapot. And because it's a saturated vapor, when it hits the cool air, the cool air just takes a little bit of energy from it, and it's condensing all the time. And so that's why to us steam seems like a visible thing. What we're really seeing is the condensation of it going back to liquid little by little, as it comes out. But like a superheated vapor, if you had that steam from the teapot go into another heating element, then that steam would rise above 100 degrees Celsius, and it would be invisible, and it would burn you really badly without you having a warning.
Is that equivalent to like the supercritical fluid? Only in a gas?
No. Supercritical fluid also requires a pressure. So all it is. Actually, I'm going to show you what happens. Let's think about phase change, and I'll talk about it when we get to it here. So phase change.
I should have called it like a desaturated vapor, because it makes sense why it's a saturated liquid. It's full of energy to the point of phase change.
Mm-hmm.
But why isn't it called like a desaturated vapor? Because it's about to lose energy to go to a phase change.
Yeah, I didn't get to name them.
Yeah. I'll fix it when I get my time machine.
Yeah, exactly. Okay, so let's look at a TV diagram, temperature specific volume diagram. So here's temperature, here's specific volume. And there's the vapor dome. And every curve or line that goes through this represents a single constant pressure. So for one pressure, you would have something that looks like this. So this line would represent a lower pressure. And for a higher pressure, it would look like this. You can see it's qualitatively very similar. And what you get is, over on this side is a liquid. Inside the vapor dome is a mix. And over here is a vapor. And so as you add internal energy to this substance, let's look at this lower one. What you get is a very small change in volume as this liquid gets hotter and hotter. Liquid just doesn't change its volume very much. We're going to often treat it like it's completely incompressible, like its density doesn't change. And so you get a small change in specific volume as the temperature rises. And then once the temperature gets to the phase change point, when that liquid is saturated, now additional energy that you put in doesn't raise the temperature at all, right? Specific saturated liquid that you add more energy to is now going through this long process of just turning into a vapor, okay? And as it turns into a vapor, you get a huge change in the specific volume. all those bonds are being broken and the molecules are spreading out a lot. Okay, so this is not really drawn to scale that well, but the specific volume of a saturated liquid is around 1,000 times smaller than the specific volume of a saturated vapor. Its volume multiplies by 1,000. And once all of that material has switched from being a saturated liquid to a saturated vapor, once you put enough energy in to make that phase change happen, now if you keep putting energy into it, it's no longer going to stay at that saturation point, that boiling point, and you're just going to make that vapor. Now the temperature is going to start going up again, and you're going to make that a superheated vapor.
So is the right point on both of those like the point at which vapor is leaving the surface of the liquid? Or is that?
Well, actually, starting here, as you add energy, liquid would, I mean, if you have it open to the surroundings, liquid would be leaving. So what you have going on in your kitchen is only in this part, really, okay? But once you get it all boiling, if you keep it in a single container, you don't let it escape, you keep heating it up, the temperature will start rising again above 100 degrees Celsius.
I'm sorry, what do those lines represent exactly?
Those are just for a single pressure. That just represents the process of more internal energy being added to a material.
Okay.
And so you can see that at first, when it's a liquid, adding energy increases the temperature and slightly increases the specific volume. But these lines are steeper than I drew them, actually. And then once you get to, so this is when the liquid gets to 100 degrees Celsius. Like you're just heating up this liquid. This is where it starts to boil. And at this point, just you keep adding energy to the liquid, and more of it is going from liquid to vapor.
So then would you say like a length of that line would be an amount of energy added?
Yeah, a length of that curve is an amount of energy. That's right. I don't, there's no reason that a centimeter here represents the same amount as a centimeter here.
Sure.
But as you go along that line, what you're doing is increasing the internal energy at a given pressure. So just remember that the one on top represents a constant higher pressure. The one on the bottom represents a constant lower pressure.
And is it the change in temperature that's leading to a change in volume?
Think of it as a change in internal energy that's leading to both of those. Okay, so internal energy is increasing as you go from left to right. The energy difference between a saturated vapor and a saturated liquid is called latent heat. So latent means, dormant, waiting to be released in some way. And the reason, so we're talking about there's a certain internal energy here and a certain internal energy here. And we're talking about the difference between those. And the reason that's called latent heat is because that is energy. It's really not heat, it's internal energy. But it's energy that is, and let's say internal energy, that is not shown by the temperature. Okay, so everywhere else on this surface, the temperature tells you what the internal energy is. Okay, but notice that inside this vapor dome, the temperature is the same for all these different internal energies. Okay, and so you can go all the way from a very high internal energy to a relatively very low internal energy without the temperature changing. And that's a super valuable region for engineering purposes. So I'll say this latent heat is valuable for engineering because, so there's, for two reasons. First, it's a lot of energy. And second, imagine a case where you have a material and the surroundings are, let's say, 81 degrees Celsius. I mean, I'm just pulling numbers out of the air. This isn't necessarily water. And let's say that the material inside here is 80 degrees Celsius, okay? And say that what you're trying to do is cause an exchange of energy from the surroundings into the system. Okay, that's something that you want to do in engineering applications a lot, is just transfer energy back and forth. Well, if that was a liquid or a superheated vapor, you could add a little bit of energy from here into the system, but every bit of energy that you're adding to here is raising the temperature. And before long, this gets to 81 degrees, and then you're done exchanging energy, okay? And so that happens, it's not very much energy that, relatively speaking, it's not very much energy that you can put in here with the temperatures close to each other like this. But if this was a saturated liquid, and this is 81 degrees and this is 80 degrees, you put in a little bit of energy, this temperature doesn't go up to 81, it stays at 80 and becomes a vapor, and you put in a little more, it stays at 80 and becomes a little more vapor. And you can pour a ton of energy in here without the temperature going up. Okay.
The only thing that happens is it all becomes vapor.
Right. And so in engineering applications, it's a pretty common thing that you're trying to use by controlling the surrounding temperature, like with a fire or something. You're trying to put energy into your system, or vice versa, but it works the same way. And so if you're right around that boiling point always with the system that you're, with your engineering system, and you can think of this as like a coolant or like the working fluid in a power plant. If you always keep that working fluid close to the boiling temperature, then you have this ability to exchange huge amount of energies without having to deal with the temperature changing. Okay, so that's why this is important for engineering. And it's also why we are not really ever going to deal with solids in this class. They just don't have that much of an engineering application. The really important engineering stuff happens at that boiling point between liquid and vapor. Okay, so the thing that I said about how weird water is, it's important for frogs that hibernate in the water, but it's not important for power plants because it's a relatively much smaller amount of latent heat between a solid and a liquid than it is between a liquid and a vapor. And so, like, what makes a good coolant for like an air conditioner or something, it's all just determined by what conditions are required to get to the boiling point. You know, you want your boiling point to be close to your operating temperature and pressure.
When you say operating pressure, like for an air conditioner, would that be like the room temperature?
For an air conditioner, let's see. I guess the room temperature is kind of the driving thing, yeah, because eventually it's going to have to release that energy through the back of the air conditioner to room temperature, yeah. And whatever pressure you need to have it, you know. I mean, I tend to think of everything in terms of like a temperature and a pressure together. So yeah, at the combinations of temperatures like atmospheric pressure, room temperature, and compressed pressure, you want something that's going to be right near that boiling point at all of those things.
Another like current heat pumps for like geothermal applications, they'll use different sets of fluids along half of the system.
Yeah.
To like make a super efficient
Uh-huh.
system. These are like latest top of the line.
Yeah. Yeah, I mean, I don't know anything about that, but I assume that like what makes, just like with everything else in engineering, what makes those working fluids useful is being able to keep them right at their boiling point and take advantage of that latent heat. Okay, so the next thing that we're going to get into is property tables. And we're going to use property tables a lot. We don't have it for every material, but we have it for a lot of valuable materials. And there are three types of tables that we'll use. The first one is saturation tables. And I mentioned before that at saturation, one property is enough to specify all the other ones. So you can look up properties if a material is at a saturation point, just as with a single index. Okay, so one property is enough to specify all the others.
Because it's a line.
Yes, exactly. At that state. And these come in two formats. You can have them indexed by temperature. and you can also have it indexed by pressure. So just depending on which one of those properties you're given. Now, when you're at saturation, you know, you can have a saturated liquid or a saturated vapor or some mix of those two. And so these are all so you have separate tables for a saturated liquid and a saturated vapor. These are the easiest to use. Because you're just looking it up by a single, index. And one thing that you always have to keep in mind when you're at saturation state or a mix between the two saturation states is what's called the quality. And quality means how much of the material is in the vapor phase. So quality is given by the variable x, and you calculate it as the mass of vapor that you have divided by the total mass, or in other words, the mass of the vapor plus the mass of the liquid. That means that if you have all saturated vapor, the quality is equal to 1. And if you have all liquid, the quality is 0. So it can only range between 0 and 1. Okay, so that's the first type of table. There's a lot of like little details or whatever, but these are the easiest ones to use. The other two are, so the second one is a compressed liquid table. And the way you look this stuff up is it's separated into sections by pressure. And then inside that section, you look it up by temperature. And then the third type is superheated vapor tables. And this works the same as the liquid tables. Works the same as the compressed liquid. Okay, so the next problem we have is in a table, you can't list continuous values. You know, you can only list a certain number of finite values. So if you're looking for a pressure of 104 bar and a temperature of 110 degrees Celsius, and they only have 102 bar for a section, and then the temperatures only get as close as 106 Celsius or whatever, what do you do to get the value you want? And we're going to use linear interpolation to get close to that. So the next thing we're going to talk about on Monday is how to use linear interpolation to use the values that are in the table to give you good approximations of the values you want. Okay, anyone have any questions about that?
So we're just like setting curves.
In a way, what we're doing, yes, we're curve fitting. Let me just draw this really quick. So if this is the real relationship between two variables, and the table only gives you this and this point, and what you want is this point, you approximate that by assuming it's a linear function that connects those two. And obviously, like the way I drew it here, you can see this happens to be a place where it's going to be a really good approximation. There's other places where, you know, if the points are here and here, it wouldn't be quite as good. But that's what we're going to do. Okay, that's all. Have a good weekend.
You too.